So let's talk a little bit about properties of, and that's supposed to be physical properties of alcohols, phenols, and ethers. Okay. And a little interesting side note, most hand sanitizers are just alcohols in gel forms, like Jell-O with an alcohol in it. So they're all very flammable. I remember when they first started coming out, I was so excited because you could write on the ground with them and then light it on fire. You probably have heard, and we're going to learn about boiling points and solubilities of alcohols, phenols, and ethers. But you probably have heard that hand sanitizers cause antimicrobial resistance to microbial resistance to antibiotics. Turns out ethanol, right, doesn't. Ethanol's mechanism for killing things is basically I destroy your cell wall and you're dead, right? But what they've done in a lot of the hand sanitizers is they've added, let's see if I've got it in here. Hang on. I thought I left it in the slides. Oh yeah, here. They've added these kinds of compounds to them. And it turns out these operate very much like antibiotics and antimicrobials. And so what's happening is by always putting a little bit of it in the hand sanitizers, they used to have it in the hand sanitizers, and people are just generically wiping it everywhere, the bacteria become resistant to that type of interaction, which then spreads to a broader spectrum of drugs, okay? So it's interesting. You can do some reading. This is all very new stuff. It's this compound, trichosan, right? This is the stuff that they used to start putting in it. It was about the mid-2006, 2005, they started recognizing this was going to be a problem. And this is probably one of the latest reviews on this subject. So I put it in the slides. If you're interested in learning about how the hand sanitizers are causing this problem, that's where you can find some of the information. The thing is, though, if it's just ethanol, there's no resistance to it. It basically dissolves the cell wall. And then, well, like if I dissolved your cell walls, right? Be like, I'm done. Okay. Anyways. And don't go around in your garage lighting it on fire like I did. It's probably not a good idea. That was the disclaimer. Okay, so we're going to learn to classify alcohols. We classify alcohols as primary, secondary, or tertiary, which I thought was interesting because I think that was on your quiz, which I have, and I need to get back to you. Yeah, so let me explain it to you now. Some people got it right, so I'm assuming he covered it in lecture. But it's in your textbook at this point. Primary alcohols, are alcohols where the carbon attached to the functional group has one carbon on it. So secondary alcohol, right? This is a secondary alcohol. Is a carbon, the one attached to the alcohol functional group, attached to two carbons. And a tertiary alcohol, right, is attached to three carbons. So let's see. You can make crazy structures, but it's easy to classify. So let me draw a couple of alcohol functional groups and see what happens. So, I need a white marker. Okay, I don't know what that is. I just made it up. I started drawing estrogen or estradiol, and I decided I can't remember it, so I just stopped. Okay, so I have two alcohol functional groups. Primary, secondary, or tertiary? Secondary, because it has two carbons attached to it. Yeah. So that's the thing. This is, if you're going to highlight these things, I don't know quite how to make this work right, but let's try this. There's 1, 2, right? So this one is secondary. So there's two carbons attached to this carbon. That's the way that works. So what about this carbon? That one's tertiary, because it's got a carbon here, carbon here, carbon here. So that one is tertiary. Good. This might come important later. I haven't had time to look forward in the book to see how they use this information. So classify these. A is, what'd you say? Secondary. Secondary, good. B is primary. C is tertiary. Yay. How is A secondary? Because you have to look to see where the O is attached to that carbon, and how many carbons attached to that carbon? 2, so it's secondary. Yeah. When we do amines, it's a different definition, and it's confusing. I'm just warning you. This one's the easy one, I think.
There's only one you don't count. You don't count the one that's attached to you. Count how many.
You don't count. Yeah, you don't count this one. You count the ones next to it. Ah. Thank you for saying that. Yeah, and this one's not really attached to it directly, so we don't count that one. Okay? So you just look at it, 1, 2 bonds to carbon, that's secondary. You look at this one, 1 bond to carbon, that's primary. Or sorry, yeah. And then this one, 1, 2, and 3 bonds, so that's tertiary. Oh, good, we were right. Sorry. I guess I don't usually leave the answer slide in there because I like writing the answers on there. Okay, so one of the things that's a feature of alcohols is they have an OH functional group. And an OH functional group means it can hydrogen bond. And do you guys remember intermolecular forces? Or you remember, sort of remember? Yeah, yeah. So let's go real quickly. I'm just going to write them out for you so you have them somewhere. Okay, so the intermolecular forces are dipole. Oops. And I tell people who are in organic chemistry and in biochem or biology, if it has an oxygen in it, it's got dipole. Okay? Oxygen is really electronegative. It's always attached to something that's less electronegative, so it becomes polar. So dipole exists between polar molecules. And in biology, you see so many things with oxygen in it, you can assume they're polar. Okay? You know, all that shape you used to, they taught you how, the shape and the geometry, and you have to look at it spatially and all that kind of stuff. If it has an oxygen in it, it's polar. The other kind is, they called it, depends on who your teacher is actually, induced dipoles. And an induced dipole is what we see between, they call it London forces. That's the last name of the guy who sort of made it a popular thing. It's not because of London, the city. This is nonpolar molecules. Okay. Lots of lipids, fats. They have some oxygen in them, but what they actually have a lot more of is just nonpolar regions. And the nonpolar regions are C's and H's, or C's bonded to C's and C's and H's. That generally makes for nonpolar. Since we're headed towards biochemistry, it's important you recognize when you see hydrocarbons, those are nonpolar. Polar groups are things with oxygen like this, okay? Or like, oh shoot, I ran out of space. Like that. Those things make for polar. Now, the last one, and probably the most important one for what we're talking about right now, and as far as intermolecular forces go, are things that can hydrogen bond. And in biology and biochemistry, it's mostly when hydrogen is bonded to oxygen or hydrogen is bonded to nitrogen that you have hydrogen bonding. And the hydrogen bond exists between the hydrogen and a lone pair of electrons on something else. and we almost always draw it as this dashed line. That's the strongest of the intermolecular forces that we deal with. So this is the strongest. And it turns out the induced dipole is the weakest. Okay. But the thing that induced dipole has going for it is it depends on molecular weight. Okay, so the bigger the molecular weight, the bigger the induced dipole. So some big biomolecules, they get molecular weights up in the millions, they have a gigantic induced dipole. Okay.
So not all molecules have a dispersion?
Oh, no, wait. So all molecules have induced dipoles,
Okay.
but not all of them have dipole-dipole or hydrogen bond.
Okay.
If you remember the discussion on induced dipole that you might have gotten a long time ago, all it needs to have is electrons and protons to have an induced dipole, which is everything. Yeah. And I can go over that in more detail if you need me to. So alcohols have, they're polar and they have hydrogen bonding. Okay, so they have strong intermolecular forces. So compared to other compounds of the same molecular weight, okay? I'll just make this note here. Compared to molecules with this approximately the same molecular weight. I'm going to say the same here just so it's faster. Alcohols have stronger intermolecular forces. And I always abbreviate intermolecular forces as IMF. So what that means is if you remember, strong intermolecular forces means they're hard to separate, right? So that means their boiling points are higher, their freezing points are higher. Okay, so strong intermolecular forces mean higher boiling points, higher freezing points. So what are molecules of the same molecular weights? Well, they could be ethers that have the same molecular weights. They could be thiols that have the same molecular weights. Alcohols will have higher boiling points than those molecules will. Just to show you, though, size of the molecule is somewhat important. So here's methanol, has a boiling point of 65. Ethanol has a boiling point of 78. It went up, right? Because it's bigger induced dipole. Right? Propanol, right, goes up. Butanol goes up. So pretty clear that as the molecules get higher in molecular weight, they all have alcohol functional groups, the boiling point goes up. Now, let me sketch a few things onto this chart. Alcohols, I gotta spell alcohols. Boiling point increases with molecular weight. Bless you. Oh yeah, I'll talk about solubility in a second. Yeah. And then, but yeah, it decreases. And I'll tell you why in a second. Now look at dimethyl ether, right? It has 2 carbons, 6 hydrogens, and an oxygen, right? Look at ethanol. 2 carbons, how many hydrogens? Plus 1, 6, and an oxygen. So ethanol and dimethyl ether are actually isomers of each other. They have the same formula. Look at the boiling points, right? Minus 23 versus 78. That's because the ether doesn't have hydrogen bonding. The hydrogen bond causes the boiling point to go up by about 100 degrees Celsius. Okay? That's in my simple math. I don't like doing lots of complicated math. Let's do this propyl. This is ethyl propyl ether, sorry. right? 5 carbons. And pentanol, 5 carbons. Boiling point, 138 degrees Celsius versus 64 degrees Celsius. Again, right, it's related to hydrogen bonding. Now, you guys remember solubility? What does it mean when something is soluble in something else? It dissolves, right? And do you remember the saying that goes with stuff that dissolves? Like dissolves like. Yeah, so let me write that out. Bless you. Or I should say, bless you. Just let it out. That's the best kind of sneeze. I inherited my sneeze from my uncle, and my children have inherited it from me, but it's like when we sneeze and we're not in class or not on a microphone, it's really loud. It scares people. So I don't know if that's an inheritable trait, but we inherited it, so there. So like dissolves like. Okay, now we're often talking about solutions with water, so alcohol in a water, right? Well, water is H, O, and H, right? So it can hydrogen bond twice. It's very strongly hydrogen bonding, and it's also very polar. Now look at a structure for an alcohol. A structure for an alcohol is like this. I'll do propanol. CH3, CH2, CH2, and then OH. So,
So always assume that they're dissolving it. Oh, okay.
yeah, so assuming it's like we're making solutions in water, right? This OH part that I'm circling here, well, this part's hydrogen bonding and polar, right? Oops. So if we're talking like dissolves like, you might look at that part of the molecule and say, oh, water, alcohol, you should be able to make a solution out of them. So, and you'll notice when you go to methanol, ethanol, propanol, for sure, right? Soluble. That means you can make solutions. You can dissolve those alcohols in water. But this part, what's that? Polar or nonpolar? It's nonpolar. Remember, I drew that little thing. That's why I drew the intermolecular force thing earlier. If it has C's and C's or C's and H's, that's a nonpolar. I'll just write it above. So you notice what happens, right? As the nonpolar part gets longer and longer, the solubility goes down and down, right? If you look at ethers, you kind of see the same things, but ethers are relatively nonpolar because of their shape. They're polar, but they're relatively nonpolar because of their shape, okay? And they start out being slightly soluble in water, slightly soluble in water, slightly soluble. When the carbon chain gets larger, it becomes insoluble. Okay? So think about it like this. Like dissolves like works because the two molecules like each other, right? So let's say you and I are friends, right? And at first, we hit it off great. We like all the same music. We like all the same shows. So like dissolves like. We make a solution. We hang out all the time together. Right? Then all of a sudden you find out I have this really nonpolar part about me. And it turns out it's a habit that I have. I don't know what it is. I'm just making it up. But this habit gets bigger and bigger and bigger, right? Eventually, so you're polar, and part of me's polar. You're kind of attracted to me, but what happens? That big nonpolar part, you don't like it. So we don't make a solution, right? So it has to do with the characteristic of the entire molecule. This part is nonpolar, and this part is polar. As the nonpolar part gets larger, it becomes less like water and is less soluble in water. Okay? What could that habit be? I don't know. What's that?
Chewing like a cow.
Chewing like a cow. Oh, yeah. Or maybe I eat earwax. You know, they make Jelly Bellies that are earwax flavored. Yeah, they make the Harry Potter ones, right?
Dirt flavor.
Dirt and worm flavor, booger, earwax. We should get those. That would be fun. I'll pass them around in a jar, and I'll have like 5 in the jar, and we'll just see, like, we'll figure out who. Can you imagine, though, the chemistry involved in figuring out what a booger tastes like? There's got to be some guy eating a booger. And they make the flavor, and they taste it, and they go, yep, that just tastes just like a booger. Hey, I've got 10 more minutes, I think, so. Yeah. No? I used my time? Well, you can read the rest of this. It's pretty straightforward. I covered the stuff at the end already. So, the guys that are coming to the lab,